Okay, so we have this equation. Okay, then the homogeneous equation. And we've got to solve the homogeneous equation, so we got a y1 and a y2, right? Homogeneous equation gives us the y1 and the y2. So the homogeneous equation is y double prime plus 25y equals 0. Okay? Well, you do the solution, and you end up with y1. A fundamental set would be y1 equals the cosine of 5t, and y2 equals the sine of 5t. Right? Now your g of t function, pretty clearly, is your tangent of 3t. It's the non-homogeneous part of the equation. Non-homogeneous term on the right, okay? And your solution is yp. Of course, the solution to your homogeneous equation is going to be an arbitrary linear combination of c1 cosine of 5t, c2 sine plus c2 sine of 5t. Okay? Your particular solution is going to be kind of a linear combination of these, but it's not linear because it's going to be using functions instead of c1 and c2. c1 times this plus c2 times this. It's u1 times y1 plus u2 y2. And now, if you just remember this and this, preferably you can rederive it, but there's some twists and turns in that derivation that I don't necessarily expect most students in an introductory differential equation to master, okay? So you can kind of understand that there's a process that's involved with the linear algebra or that's solvable by some linear algebra, okay? You can solve it other ways. But what it comes down to is this, okay? And then the final result, this. Now, if you remember this, you can get this, right? Right. If you just remember this, you're okay. But somehow, and actually when I wrote this, I wrote something kind of obvious. I meant to put these terms in for the U1 prime and the U2 prime, right? Right. I mean, that's implicit. So I didn't actually make a mistake, but I actually didn't write what I intended to.
That's not
okay? So I'm going to write it now, where U1 is then the integral of minus y2 g over the Wronskian, and I'll write the Wronskian, y1, y2 prime minus y2, y1 prime with respect to t, and u2 is the integral of y1g over y1, y2 prime minus y2, y1 prime dt. Now from this you can see that the integral could get pretty nasty, okay? Because this denominator could be a pretty ugly function, okay? Although usually it's going to involve exponentials and sines and cosines. When it involves sines and cosines, often it'll maybe even turn out to be constant, okay, which it does in this case. The Wronskian of this is just 1, okay? So the Wronskian is going to be particularly simple for this example. Don't expect it to always be simple. And then our y2g is going to be a cosine times a tangent, right? Or sorry, y1g is going to be a cosine times a tangent. The y2g is going to be a sine times a tangent, right? Now it's not going to be the cosine of the same expression, so things are going to get a little complicated when you start doing the integral, right? But it's going to be manageable for this particular function. For other functions, less so. I could have chosen tangent of 5t here, And that would have made things even simpler.
Right.
But I don't want you to get the idea that they're always that simple. Okay?
Okay.
So write out the integrals. We're not going to have time to actually do them, but write them out and think about how you would perform the integration. And if you have to leave it in the form, yeah, that could be integrated, but I don't have time between Tuesday and Thursday to review trigonometric integration to get the tricks I need to do this, right? Although you should, because you need the trigonometric manipulations to solve important equations, which in this case are the equations for simple harmonic, damped simple harmonic motion, damped harmonic motion, or damped simple harmonic, I guess, and RLC circuits, okay? And all the implications of those solutions right at the end of chapter 4. Okay? So, go ahead and write out the integrals and see why you don't really want to mess with them right now.
Okay.